you are going to have an ecosystem model. Then boundary conditions. These boundary conditions can be at the surface and at a certain depth if you are only interested in only a certain level of the water column. And you can set, for example, Neumann boundary conditions, so at the surface and at the bottom. So basically, whatever comes in goes out at these boundary conditions. Or you can also set some values, for example, for nutrients. If you have some observations, you can set it for observations to better capture what's happening in terms of living concentrations. It's generally preferred to set initial conditions based on observations. So if you have enough observations, you try to set it as close to observations to remove the uncertainty that may come from initial conditions. I use some BATS data to set the biomass profiles. And I want to go over some definitions. When we talk about models, we talk about parameterization. Parameterization is really a model within a model. For example, the growth rate of phytoplankton. As I have shown you, growth of phytoplankton is a very complicated process, but we set it to a constant value, the maximum growth rate. So we have parameterized what's happening in the nature. Okay, and calibration. In most models, we adjust them and we try to match the dependent variables with observations. So we tune the models, we can change these parameters to match the observations. Of course, this should be done within the observed limits. And in order to produce results, you need to do discretization in space and in time. Okay. So to understand what's going to happen to the biomass of phytoplankton in this point, you need to know how much phytoplankton would come into this level from above or from below. Okay. This can be done. This transfer can happen because of advection or mixing. So you need to improve these. And also, in order to estimate what's going to happen at a later times that you do this discretization in time. I will show you how we'll do this. You write the governing equation that I have shown you in finite difference form. It's very simple. To understand what's going to be the biomass of a certain phytoplankton at a later time step, you need to know its biomass at the present time step. Then you add or subtract what's coming from above and what's coming from below. Okay? And then you add the source and biological source and symptoms. So under those environmental conditions, what's happening to this phytoplankton? Is it growing? Is it dying? Is it being replaced by zooplankton? So this way you can estimate what's going to happen in the next time step. We need to use this finite difference forms because most of the equations that we use, the governing equations, you cannot solve them. There are no finite solutions for them. So you need to solve them numerically. Okay, and as I told you, I was going to talk about the challenges that the modelers are facing. And I would like to very briefly talk about model verification or validation as we use today. First of all, the input parameters are not completely known. This is one of the main challenges that we are facing. And then the problem of scaling comes, that the other speakers also talked about this. Doesn't matter if you are dealing with model or with measurements. Generally, we do these measurements at very smaller scales than what model measures, and we often assume that we often extrapolate what we see to larger scales. Also, observations that we compare with our models are subject to errors. And that more than one model can produce a given result. So you can have a result for a wrong reason. This is called underdetermination when you face a problem like that in science, okay, because you don't know, you cannot identify what to believe. It's possible that you set your mortality, okay, your model doesn't fit the observations, you can increase your growth rate a little bit, so your primary correction matches the observations, or what you can do, you can reduce the mortality term a little bit and then it may match. Of course, you need to then look at what's happening in the other compartments, etc. But it's possible that different models with different parameters can give the same result. And when this happens, generally the personal bias comes into play. Okay, it depends on the preference of the modeler, which way to choose. And I think Hezi also referenced to this paper. He was very critical about the modeling practices, and he was claiming that it was all about some not tweaking, like all the results were obtained because the modeler thought that's what should have been done, and the models include a lot of adjustment and a lot of tuning. And the main danger of this is that you can capture what the data is showing for the time period that you are tuning your model, but if you want to extend your model to other places or other time frames, then your model may fail. And verification means establishment of truth. Okay, so today we talk about model validation. Actually, validation means establishment of if your model is legitimate or not. What I mean, if your model is legitimate or not, if you have sound mathematical equations, if they don't have any errors, if your model doesn't have any bugs in it, if you get the same results in different computers, this is validation. But today we talk about validation. We use verification and validation interchangeably. Also, I think that we shouldn't even be talking about verification because we cannot verify a model. We should be talking about model evaluation. But model validation has become standard language, so I gave up discussing about that. And it's the nomenclature nowadays. You can see Karselen has a couple of good papers on how model skill assessment can be made. In a recent project now, we have defined we tried to constrain how we validate our models. For example, we say that the model is validated, at least it serves our purposes, if it captures the seasonal cycle of phytoplankton, if the bloom time and the bloom period fits the observations. And you can also use some statistical analysis like target diagrams or Taylor diagrams or self-organizing plots. But please check this paper and other papers like yours if you're interested in model skill assessment. I will not go into that. But Raghu was mentioning, we need to really heavily evaluate our models, and we need to be honest towards the community if we don't want to lose any credit, so they can trust us. And in terms of the predictability power of the models, we should also be honest, and we should say what the model can capture and what it cannot. Okay, the other challenges that are awaiting us is that often there is a trade-off between biogeochemical function versus ecological function of a process that we include in models. For example, PMS producers can be important, but when we include GMS producers in our models, generally we focus on how much GMS they are producing and if they are doing it in the right way. But their ecological function, how they influence the marine ecosystem, is often overlooked. Same is true for calcifiers that are included in the models. Generally, we assume that they're coccolithophoros. And big zooplankton are defined as sinking parameters in sinking compartments in the models, and their trophic interactions are not detailed. And benthic suspension and opposite feeders, some models include them, but most models are missing them. And there are new discoveries. For example, the microbial is not that new, but we need to carefully include them in the models. Iron is being included, although there are still many uncertainties included with that. Ocean classification is another process that models are trying to capture. Nitrogen fixation, biogenic gases, and bacteriology by cyanobacteria. It's really not in the models. And mixotrophy. This is quite important, I believe, and because there are certain plankton that can both do photosynthesis, but also can go and graze on other cells. Okay, these all increase model complexity, and we try to include these in the models to increase their predictive capacity, because the predictive capacity increases if your model can respond to different environmental conditions in the future, right? But often we don't know enough about all these processes to include them in the models. The other thing is that we really need to pay attention is the trophic interactions between different compartments, especially if we are talking about end-to-end models. And then the question arises if we can go beyond some toys that are based on experimentation or trial or error methods. There are many ideas, but my philosophy is to focus on, of course, global models are very useful, and Lauren will talk about these, but it's also very important to tackle certain research questions by reducing the spatial, not the spatial resolution, but the area that you're looking at, and define a very precise scientific question, and depending on that scientific question, you need to set up your model system. For example, if you are interested, this is a diagram that shows trophic level versus functional complexity. If your focus is on zooplankton with a life history, you can have more complexity in your model at this level, but at the end you need to include also predators, but you can get away with having less complexity at this level. Or if you are looking at primary production, then you may need to have a model at zooplankton level, but not with a strong life history, and you need to include the chemistry, of course, and you may not need to go up to the predator level. Okay, of course this is, this is a good paper. I didn't send this as a reading material, but you can have a look at it. It's a science paper. And if you have any other ideas or any questions, or if you disagree, of course, feel free to speak up. And there are new ideas about going beyond MPZP type modeling. One of them is the Darwin model proposed by Ms. Bolos. I think Shuwei yesterday at a postron, and she's planning to use model in North Atlantic. What this does, it generates multiple phytoplankton types,